Okay, welcome to Math Stat 345. Oh, sorry, not 345, sorry. Math Stat 341. This is the second class of the semester. And what I want to do today is I want to continue some of the stuff we were doing from chapter 1. All right, so hopefully everybody can see the screen. I've got it on my laptop as well, so I should hopefully be able to see what you're doing. And I should hopefully be able to see anybody who is trying to say anything. But if not, just please speak up in the chat. Hopefully everybody remembers how to handle a Zoom class. All right, so what I want to do today is I want to review a bunch of stuff. I want to review factorials, binomials, choosings. These are stuff you should have seen in high school classes, maybe in an Algebra 2, maybe in a pre-calculus. So I'm going to go through them fairly quickly. But again, if you have questions, please talk to the TAs, talk to me. We've arranged to have TA sessions, I believe, every day. As time permits, I'll talk a little bit about other related things like QWERTY and Babylonian mathematics. I want to do a quick review, as I said, of combinatorics, as well as a quick review of integration. So one of the reasons multivariable calculus is a prereq for this course is that I want to be able to integrate certain functions. Sometimes functions of 2 variables, most of the time it'll be functions of 1 variable. There are 2 main themes in calculus. There's Calc 1, or differentiation, where the tangent line or the derivative gives you a really good approximation locally of the function. And the idea is locally, any function looks like a straight line. And then there's integration, that the area under the curve can be given by computing antiderivatives. And this is the main reason we care about integration, is it gives us probabilities. These areas are probabilities. In general, it is extremely hard to integrate and get a closed form answer, which is sad because we'd love to see how answers change as we vary parameters. So we have to do a lot of work to come up with nice distributions where we have closed form expressions for everything. And so I'll talk a little bit about some integration techniques and just see if your least favorite techniques are my least favorite techniques as well. For the most part, I will confine myself to integration by parts, but this is the 21st century. Everybody should be able to use something like Wolfram Alpha or some such to just evaluate integrals like this. I really want to emphasize today the power of coding. And so in the 21st century, code is very easy to write and execute. And this is something you need to be able to do. So I think most of you do have experience with coding. If you don't, I am happy to do some additional classes for those who want it on coding, to meet with people. You really want to leave this class being able to code well. I do not care which environment you use. I often use Mathematica because I like the graphical interface. I was trained as a number theorist and it has a lot of good functions predefined, but there's a variety of things you can use. If you're taking this as Stat 341, you want to make sure you know how to do all of this stuff in R. So some general items as well for today is I want to try to emphasize the difference between a formula and a useful formula. A lot of times we can write down the answer to a problem, but it may not be an easy calculation to do. It may be hard to extract. Frequently, instead of doing the calculations, we often simulate. And again, this goes back to the ability to code. You want to be able to write simple programs to do lots of trials. And if you can do 1,000,000 trials, 1,000,000,000 trials, you often have a pretty good sense of what the answer is. And then I want you to think very hard whenever you're introducing some notation. Is this good notation? What does it emphasize? Is it easy to read? Is it easy to look at and understand what you're doing? This is especially important when you're choosing names of variables. You want to be able to follow the arguments without too much trouble. If there's time today, I want to talk a little bit about sniffing out formulas. So I believe in the book, we talk about how you would sniff out the product rule without actually proving it. Just why is something like this reasonable? And I believe the book also talks a little bit about how to sniff out the rule for what is the probability of A union B in terms of other events, in terms of simpler events. As you go further and further, you're not going to be told what the answer is. You're going to have to try to figure out, what do you try to prove? What do you think is going to be useful? A lot of this is you do simulations, you gather data. This should be one of your default go-to mentalities. I'm going to collect some data and try to see if I can conjecture something, if I can see a pattern. And then once you have that idea, then see if you can prove it. And as always, if you have any questions, please just speak up. So the next is just, this is on the web, this is the homework that's due February 20th. So you should know that that date is in the future. It's not too close. I want to make sure you have plenty of time to do the homework problems and talk to the TAs, talk to me, talk to each other if you have questions. Homework should be neat. If you're doing it and handing in a physical copy, it should be stapled. If you work with people, if you use any online sources, just state who you worked with. The more the merrier. That's absolutely fine, but just state who you're working with. Do the problems in order. If you don't know how to do something, talk to us. And if you don't have time, just skip it. But don't have the problems all out of order. It makes it a lot harder to grade and follow what you're doing. Okay, so again, this is also online, but I just wanted to put in the slides as well, which will be posted. Okay, so we talked briefly about the birthday problem in the first class. And I want to go through this in a little bit more detail and go through the argument in the book to try to estimate what is the probability that if everybody is equally likely to have any day as their birthday, how many people do we need to have in the room before we have a 50% chance that two people share a birthday? And again, we talked about how important it is to be clear on what the assumptions are. My wife is an identical twin, as I remarked. When we go to gatherings on her side, it's almost 100% certainty that there's going to be at least two people sharing a birthday. So we will assume all days, equally likely. And then what we can do is we can do the more general case. Let's assume we have some number of days in the year. Anybody want to tell me what letter we should use to denote the number of days in the year?
D.
What letter?
D.
D. So assume D days in a year. The only thing that might be bad about using the letter D, and again, I'm going to use D, is that if we have any derivatives coming in, D could be confused for derivatives, but I think D is a really good choice. So we want to calculate what is the probability that two people share a birthday when we have n people. And so we can imagine the people coming in one at a time. And for a lot of things in probability, it's often easy to calculate the probability something doesn't happen and then the probability happens is 1 minus that. So what's the probability no two of n share a birthday with D days in a year? Now, the reason this is so much easier is, can somebody tell me some ways you could have two people sharing a birthday? Yes.
Like only two persons share birthday, and like B person share birthday, B minus one, B minus
Good.
two.
So you could have two people, three people, four people sharing a birthday. You could also have multiple pairs of two or three or four sharing a birthday. There's so many different ways that this could happen. Frequently, it's much easier to calculate the probability that it doesn't happen. So for instance, if you want to calculate in poker, what's the probability you have at least two kings? It's easy to calculate what's the probability you have, 0 or 1 king, maybe. Okay, so let's look at the probability that no two share a birthday. When the first person walks in, how many possible days do they have? All the days. And now the next person walks in. They can't share the same birthday as the first person, so how many days are available?
D minus 1.
D minus 1. And you keep going all the way down until D minus n minus 1. And it's annoying. So instead of writing it as D over D, how should I write the first term? So I have D minus 1 all the way down to D minus n minus 1. I should write the first term as what? D minus
Zero.
D minus 0. And so what I can do is I can write this in product notation. Product notation is very similar to sum notation. So it's going to be the product k goes from 0 to n minus 1 of d minus k over d. And by writing it like this, it just makes it a little bit clearer how I'm writing the product. Well, this is the same as the product k goes from 0 to n minus 1 of 1 over k minus d. Can someone tell me what Pavlov is famous for? So this is a liberal arts college. Anything is fair game.
Conditioning dogs to salivate when they hear a bell.
Yes. And so, you know, I don't expect you to salivate when you see a logarithm, but I do expect you to have a reaction. Whenever you see a logarithm, you should, I'm sorry, whenever you see a product, you should think logarithms. So product, think logarithm. And so I'm going to define this probability to be Q sub n, and I'll put a capital D to remind myself that this is with D days in the year. Okay, the colon means it's a definition. So this is nice math notation. The colon just means definition. All right, so what we can do is we can try to analyze this. So we have Q and D is the product k goes from 0 to n minus 1 of 1 minus k over d. So the log of Q and D is going to be the log of the product k goes from 1 to n, from 0 to n minus 1 of 1 over k minus d, which is the same as the sum k goes from 0 to n minus 1 of the log of 1 minus k over d. And now we see why the logarithm was such a good thing to do here. The log of a product is the sum of the logs. We have a lot of understanding of logs. So by Taylor's theorem, the log of 1 minus x, this is one of the expansions you should know, is just negative x minus x squared over 2 minus x cubed over 3 minus x to the 4th over 4, dot, dot, dot. And in general, the Taylor series of f at 0 is going to be the sum of the nth derivative at 0, x to the n over n factorial, n goes from 0 to infinity. And then it's a big question as to when does the Taylor series converge? And the expansion we have above will be absolutely fine for the absolute value of x less than 1. So to first order, we get the log of 1 minus x is negative x. Better is negative x minus x squared over 2. So as a nice exercise, you can go through and try to redo the birthday problem, keeping that next term. So for those of you who are physicists or taking physics classes, you often do these series expansions, and you can try to see how much of a difference does it make to keep those extra terms. So right now, we would get the log of Q and D would be equal to the sum k goes from 0 to n minus 1 of negative k over d. What kind of number is the left-hand side? So when you look at this number, what kind of number is it? Can you tell me anything about it? Could this equal 3?
No,
Why not?
that's going to be a negative number, I think.
Perfect. It's got to be negative. You know, when k is 0, it's 0. Otherwise, every other term is negative. What about this side? Is this negative?
Well, they're equal to each other, so it's got to be negative.
It's got to be negative. But we might have made an algebra mistake.
Okay.
Whenever possible, you want to check your work and ask yourself, is this reasonable? Can I do
So
a smell test?
because the probability is less than 1, it's going to be
Good.
negative.
probability less than 1, so the log is negative. This is not a proof that I have not made an algebra mistake. I've been reading applications to small since 3 a.m. today, and then went on a jog with one of my former Williams students who tried to run me to death. So I'm quite tired at this point. I could easily make an algebra mistake. So whenever possible, I do some quick checks. Okay, nope, this is looking reasonable. This is the same as negative the sum. K goes from 0 to n minus 1 of k. And there's a beautiful, 1 over d with a negative sign. I'm pulling out the d. And there's a beautiful formula for the sum of the integers from 0 to n minus 1. It's just going to be n minus 1 times n over 2. And so I'll just do this as a quick aside. Let's let Sm be 0 plus 1 all the way up to m. If you write the numbers backwards, m plus m minus 1 plus 0. And now if you add, you get twice Sm, and then each sum is m, and you have m plus 1 of them. So it's m plus 1. Therefore, Sm is m plus 1 over 2. So this is a nice quick trick to find what is the sum of the first m integers. You can do something, you can also prove this by induction, and induction works better if you want to do sums of squares and whatnot. All right, so I've got a formula for the log of Q and D. And so I now have the log of Q and D is equal to negative 1 over D times n minus 1 times n. And I want to find n such that Q and D equals 1/2. So I would get the log of 1/2 is negative 1 over D n minus 1 times n. What's the log of 1/2? Who remembers their log laws? This is just negative log 2, and I think that's about negative 0.69 if memory serves. I will quickly check on Mathematica. The log of 2, yeah, 0.693147. There are certain numbers that you should remember. In the 21st century, you can always quickly go to the computer. So it's about 0.69. So we get that n minus 1 times n equals d times the log of 2. How can we solve this? So how would you solve this? We're trying to solve for n. We know n minus 1 times n equals d log 2. How could we solve?
We could take the derivative and set to 0.
We can't take the derivative because we're trying to solve for n. So if you take the derivative, you'd be trying to find maybe some kind of critical point, but we're trying to find the n where this expression over here had q and d equal 1/2. So we're trying to find that special value of n. So
we could distribute and just solve algebraically.
yeah, and what's the method you would use to solve that? You would use what?
Called quadratic equation.
Right, the quadratic formula. I don't want to use the quadratic formula because that's going to involve messy square roots. What I'm going to do is I'm going to say n minus 1 times n is approximately n minus 1/2 squared, because that's going to be n squared minus n plus 1/4. That's almost n minus 1 times n. Why did I take n minus 1/2? Well, here is n minus 1. Here's n minus 1/2. I just split things in the middle. Again, you should use the quadratic formula, but it's good to be able to do these quick back of the envelope calculations. That would give me n minus 1/2 squared is approximately d log 2, or n is approximately d log 2 plus 1/2. Square root of d log 2. So n is approximately log 2 to the 1/2 square root of d, well, I'll write it this way. D to the 1/2 plus 1/2. And this is the most important part. The critical n grows like d to the 1/2. And now you can write some code, you can do some simulations, and you will see phenomenal fit to d equals 1/2. That's the important thing as to how does it grow with the number of days in the year. And so if you take d equals 365, you get n is around 21, give or take. I forget exactly. It's somewhere between 21 and 22, I think. And so this is the birthday problem. It's one of my favorite problems. It has a lot of interesting applications in the real world. But what's great about this is it shows you a lot of key algebra techniques that are very useful for problems like this. We had to find a way to sum the first n integers. We had to use Taylor series to approximate the logarithm with something simpler. We had to take the log of a product to make it understandable, to make it easy. It was very hard to calculate the probability of at least 2 people sharing a birthday, but it was much easier to calculate the probability that 2 people don't share a birthday. So there's a lot of really good stuff to think about. And then, of course, you could start asking about generalizations. What if you wanted at least 3 people to share a birthday? How hard would that be? What if you wanted 2 pairs? How hard would that be? What if you just wanted people to be within a day of sharing a birthday? Or maybe within a month? You know, it's very different if you say they have to be born in the same calendar month or just within 30 days. So whenever you have a problem, always ask, how can I push this? What else can I look at? Okay. So what I want to do now is I want everyone to choose 2 distinct days randomly in the year. Okay, so given that everybody is zooming in, you should be able to write this down, write down 2 days in the year. I will give everybody 15 seconds to do this. Choose the days completely at randomly if you can. I debated queuing up the Jeopardy music, but I decided not to. All right. What I would like you to do is calculate the difference between the 2 dates. And so what I've just done is in the chat, I've actually put in a link to calculate the distance between 2 days. And I'm sending it to everybody right now by email as well, so you have it in both places. So I'll give everybody a minute to calculate the distance between the 2 days. All right. Has everybody calculated the differences between the 2 days? All right. Before I have you give me the answer, does anybody want to be really brave? And again, you can only gain points for this. You can't lose points. Does anybody want to conjecture what the average separation should be between your 2 days? And again, when you're doing the calculation, January 1st is not close to December 31st. We're not wrapping it around. Anybody brave and want to conjecture? If you don't want to conjecture, give me at least an upper bound. It can be a bad upper bound. I'm sorry?
6 months.
6 months. Okay. So we have a conjecture of 6 months. That's a very reasonable conjecture. Anybody want to give me another conjecture or an upper bound? It's okay if it's a trivial upper bound. Everybody should be able to give me a trivial upper bound right now.
12 months.
12 months, right? And I like how you said that because then we don't have to worry about February 21st. Oh, sorry, February 29th. Upper bound, 1 year. Or maybe minus a day. How about a lower bound?
One day.
1 day, right? So again, always have trivial answers, upper bounds, lower bounds that you can get trivially, and then let's see if we can do better. Anybody else want to make a conjecture other than 6 months?
So I don't really have any principled reason to think this, but I think it's less than 6 months. I would,
Oh.
My conjecture is that it's going to be maybe 4 or 5 months, or less.
Any idea why?
I haven't no real clue at the moment, but I'm trying to think where that intuition comes from.
So imagine we have a circle and we have day 1, day 2, ... day 365. And we choose 2 days at random. Okay? Without loss of generality, we can spin the circle so that the 2 days just move and keep their relative separation. You might as well assume the first day chosen is January 1st. And then you choose the second day randomly. And if we're looking at things wrapped around where you can measure in either direction, what would you expect on average the separation to be in that case?
3 months.
I'm sorry?
3 months.
Why 3 months?
Because the maximum separation would be 6 months.
Good.
And then, yeah.
So maximum separation is 6 months. So half that, or 3 months. So if we had the wraparound, we might expect something on the order of 3 months. Now, if we don't have the wraparound, where do we expect things to be? Well, now we have something that's more linear. 1, 2, ... 365. If we were to just choose one birthday, where would you expect the one birthday to be in the year? If you could only choose one number, where do you think that would land? Wouldn't you expect it to land about in the middle? If you could only choose one number, that's probably in the middle. But now we're choosing 2 numbers. If I could choose 2 numbers, maybe I expect the first number to be roughly 1/3 of the way, and the second number maybe 2/3 of the way. To me, that seems somewhat reasonable. And if I do that, then the separation would be 1/3. Right? Or 4 months. Or approximately 120 days. Versus 3 months, which would be around 90 days. So again, this is just a complete heuristic. Okay? So what I want people to do now is just say the dates you have, the separation, one at a time, and I'll just type them in. So if people can just start talking, don't talk over each other. I trust you to do this. Let's go.
April 1st and July.
No. Just give me the difference. Give me the difference. You're supposed to use the website to calculate the difference.
91 days.
Okay, 91. Next.
93 days.
93. Next.
142.
142. Next.
305.
305. Next.
158.
158. Next.
292.
292, next.
4.
4, next.
196.
196, next.
198.
198, next.
76.
100.
Wait, 76?
Yeah.
Okay, next.
134.
134, next.
3 days.
3 days?
Oh
Was that 3 days?
Yeah.
Okay, next.
191.
191, next. All right, do I have everybody? All right. So if I calculate the mean, I get 144.846. So the class mean was 144.846. How do you think that compares to my estimate of 120 days? You know, you're trying to decide right now, is it worth taking probability with Miller? Does this guy have anything worth, you know, teaching me? Or is this a complete waste of time? You know, I'm doing real world data with a very small data set. You know, we had what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We had 13 data points. I can actually go through and do the calculations that it is of 1/3. And so I will just quickly, no, I'm not going to bother switching. So I think I'm sharing the video here. So, you know, as a mathematician, whenever you get, you know, envelopes or pieces of paper, you always use it to do calculations. And so just, you know, quickly, it's just involving some simple calculations involving sums of integers and squares of integers. If there's interest and time later, I'll show you how to do it. It's not too bad, or it's a good extra credit problem to see if you can do this. What I want to do now is I want to talk about some code to test this. So I unfortunately cannot get 1 million students in my class. My TAs are actually very grateful that we don't have 1 million students in the class. The homework would be a nightmare. Here is a simple program in Mathematica. One of the things you hopefully notice is this comments. When you are writing code, please include comments so people can follow what you're doing. Mathematica puts the comments in a different color. You start a comment and end a comment with these, you know, parentheses, star, star, parentheses. And then I'm defining 2 quantities, the spread and the square spread. So these are going to be the difference between the 2 days and the square of the difference between the 2 days. And I calculate both. D is going to be the number of days in the year. And then my input is the number of days in the year and then the number of iterations I want to do. And as n goes from 1 to the number of iterations, what I do is I randomly choose 2 days in the year. And then after I choose the 2 days, I calculate the difference between them. And I take the absolute value so I don't have to worry about which one was first, which one was second. And then I take that value and I add that to my list of spread. And then I take the square of that and I add that to the square of spread. And then I just go through and I just print out the mean of spread and the mean of square spread. So I know there's at least one person in Zoomland who has good coding skills. Does anybody see anything bad about this code? Very straightforward, but there's something truly disastrous about it.
I have a question.
Yes.
How do we make sure the first day will be larger than the second one?
We don't. That's why I'm taking the absolute value.
Oh, wait, oh, gotcha. Thank you.
Yep. And so rather than, you know, risking sorting them, which I could do, I'm just taking the absolute value. But that's also one of the nice things about looking at the square is because when I look at the square, then I don't have to worry about which one was first and which one was second. So does anybody notice anything bad about this code? It's very simple. It's not doing anything that's too complicated. So one of the things that we struggle with as professors, and this is a 300 level class, so we can have these conversations, and in fact, we should have these conversations, is what is the value added? Especially when we're looking at problems like this, I need to justify you're coming to class. There should be something you're gaining. So this is a chance to really talk and try to emphasize some subtle points. You are all smart, or you would not be here at Williams. You would not be in a 300 level math stat class. So I'm expecting you to read the book. I'm expecting you to come to class prepared, having looked at the definitions and mastered the basic material. If you have questions, let me and the TAs know. I really want to go over the more interesting, difficult stuff and try to give you a few things that you can use for the rest of your careers, either in academia or industry, as well as just observe some fun things. This code looks really good, but there's a huge difference between doing pure math and doing applied math. In applied math, we worry about runtime. We worry about efficiency. Factorization is trivial. If I want to factor a number, I just have to try all the numbers smaller than it and see which go in. But in principle, that's an absolutely disastrous algorithm to use. And so let's look and see how long it takes to run this program. So I'm going to calculate 10 to the m simulations. M goes from 1 to 6. So I'm going to do 10, 100, 1,000, 10,000. When I take 10 and 100, it runs so fast, Mathematica can't even detect how long it took the program to run. It's effectively 0 time. When I get up to 1,000, the runtime was 0.0156 seconds. At this point, I'm not convinced that that's exactly how long it takes. It matters what else is my computer doing. It's pretty fast. If I go up by another factor of 10, it's now 0.21 seconds. That's not a terrible growth rate. It grew by about a factor of 10. But the real question is, how is it going to continue to grow as I go higher and higher up? Is it going to grow linearly? Is it going to grow exponentially? Well, let's find out. And so, at 1,000, it was 0.015. At 10,000, it was 0.21. At 100,000, it was 29. So it goes from a little bit more than a factor of 10 to now a little bit more than a factor of 100. And now over here, to go from 29 to 76 seconds, I need a new color. If I multiplied by 100, that would be not enough. This is going to be now greater than a factor of 200. I'm getting really worried about how long this is going to take. It shouldn't be taking me that long. What's the problem? The problem is, if you look at the code, what I'm doing is I have lists. Lists are expensive. I'm storing all the data in a list, and the longer I run the program, the longer the list is, the harder it is to work with it. If I now, this is actually better because it gives me all the data and it gives me the data in order. But because I'm saving so much stuff, there is a significant degradation in runtime. If I really cared about not just what the average spread was, but the distribution, how many times was the spread 1, 2, 3, 4, better is I could do an array. And what I could do is I could do array spread of difference plus plus. That would mean increment the array value in that spot by 1 to indicate that we just found a difference of that. And that would be much more compact. I would only have to save D elements there, rather than a list that's getting longer and longer and longer the more iterations we do. So that's why this is such a bad program. It doesn't look horrible. And again, If you just do pure theory, it's fine, it works. But if you want to implement it, it gets very bad. So here is a slight tweak. All that I've done now is instead of having arrays, these are now numbers. And by switching them to numbers instead of arrays, the runtime is much better. At 10 to the 4th, it was 0.03 seconds for the faster way versus the 0.265 for the slower. If I go up to 10 to the 5, it was only 0.375 seconds. This was basically a factor of 10. Much better than the 29.7. If I go up even further, I'm now going to just look at the faster one. If I go from 10 to the 7, that was about 48 seconds, 10 to the 8th, about 405, 10 to the 9th, 3861. These are roughly factors of 10, which is what you would expect when you run it 10 times longer. So this is telling us this is a much better way to do things. When you're trying to get data to make conjectures, the more data you get, the better. So if you're going to do coding, you need to have some efficiency, or it's going to greatly hinder how much you can do. Most of us are not that patient to wait, 7,600 seconds. That's about 2 hours. And that's just to do 1 million. If I wanted to do 10 million, oh Lord, that would be terrible. Whereas over here, I'm getting 10 to the 9th now in a little bit over an hour versus 10 to the 6th. That's much better. So I'm getting 3 orders of magnitude greater in half the time. So this is the main point I want to emphasize for today, is just the need to be able to write simple code well so you can investigate further. A lot of students are interested in careers in industry and consulting and whatnot. There's lots of questions you can get asked. Here's a fun practice question. So you have a fair 6-sided die numbered 1, 2, 3, 4, 5, 6. All numbers equally likely, and you're paid the same amount of dollars as the number that you roll. So if you roll a 5, you get $5. If you roll a 1, you get $1. How much would you be willing to play the game? And again, it could make a difference that you're playing the game only once or you're playing the game many, many times. Because if you're playing it only once, you might be risk averse. But if you're playing it 1 billion times, the central limit theorem, which we'll talk about in greater detail later in the semester, will kick in. Anybody have a rough idea of how much you might be willing to be indifferent to playing the game?
I think it would be $3.50.
Yeah, I mean, the average value is going to be 3.5. The 1 and the 6, the 2 and the 5, the 3 and the 4, they all average 3.5. So you would expect to get $3.5. So if you pay $3.5, you should be indifferent. If you can play the game for less than 3.5, then you would expect to make money if you play it a lot. Let's tweak the game. It's always fun to tweak things. So now you can roll the die twice. So you can either keep your first roll, or if you don't like it, you can roll again, but then you have to take the second roll. How much would you be willing to pay now? More or less than 3.5?
More.
More. Why more?
Because if you get a low roll, you can just roll again. In principle, whenever you get to 1, you can just be like, I'll roll again, and expected value would get 3.5.
Right. So if you got a really bad roll, then you have a chance of rolling again. It can't be worse to have a second roll. Right? Give me a really simple strategy to prove it can't be worse to have the option of the second roll.
You could just always take the first roll.
You can just always take the first roll, right? So unless you're somehow tricked, and again, I have met professional magicians who are terrific at finding ways to trick people, but if you do things well, it can't hurt you to have more opportunities. It can if you misevaluate the opportunities. but it can't hurt you to have more opportunities. So it should be more than 3.5. How much more? Well, you have given me a great strategy. If it's below a 3.5, roll the die again. So if it's a 1, 2, or 3, roll again. And so you can do the math and you can calculate what it should be. You could also write some code. And so I won't go through and do the math right now. I will just display, here's some simple code I wrote in Mathematica to just do this a huge number of times and just, keep track of what we get. And so looking at this, I'm learning on average 4.25225, 4.25142, 4.25001. It's looking like 4.25. It's looking, a lot like 4.25. And so as a nice exercise, try to prove that it is 4.25. With simple code like this, I'm able to do 1 billion times in 182 seconds. And again, you can see very much, the factor of 10 growth in runtime, which is what you would expect for a nice simple problem like this as I do more iterations. We don't want to save things as lists. We don't want to have these massive streams of data. All we care about is what we're getting on average. Okay, any question on the coding we've done so far? So this is the level of coding I want you to be able to do. I want you to be able to write simple code to get a feel for what's going on. Okay, so you are supposed to know calculus. So I have a bunch of handouts that I have online. The first one has a bunch of worked out calculus problems where it lists all the problems first, and then after that, it lists the solutions. So basic differentiation, basic integration, you should make sure you know how to do stuff like this. The goal of this class is not to come up with painful integration problems for you. The goal is to use these techniques to solve problems we care about in probability. And so for most of the time, I don't care if you use a program to do these integrals, but you should know how to do some of the basic stuff. Okay, so actually, let me just, before going on, can anybody tell me who's brave what their least favorite integration method is?
Integration by parts.
So you're allowed to say that, but I think there's something much worse than integration by parts. It might be so bad that you've become traumatized and forgot that you learned it. Anybody have any other integration techniques they don't like? How many of you remember partial fractions? I think that's the most painful of the integration techniques that you learn in high school. How many of you did not learn integration with partial fractions? Here, just put something in the chat if you have not done partial fractions. So I'm not going to try to give you difficult technical problems in calculus. It's good to know how to do stuff like this. But again, the goal of this class is to use these to do various things. So some of the key methods is change of variables or U substitution, trig substitution, integration by parts or the product rule, partial fractions, converting to a double integral. We'll talk a little bit about that. That's a strange technique. Differentiating under the integral sign, that's a very powerful method. And then the bring it over method. If you want some more stuff about this, I go into a little bit more detail as well as do some of the coding in a lecture that I gave in the 2021 version of this class. So let me just quickly remind you of where integration by parts comes from. So again, this is supposed to be a review of stuff you've seen before. If you're not comfortable with this, I'm sounding like a broken record, talk to me, talk to the TAs. So all of the integration rules come from rules from differentiation. So somehow we know how to do a derivative and we can convert that to a rule about integration. So in differentiation, we would have f times g prime is f prime g plus fg prime. when we write it as an integration rule, we replace f with u and g with v, and we get u prime v plus uv prime. And how does this become an integration rule? Well, if I give you the integral of uv prime, that's really easy. What function has derivative, the derivative of u times v? It's the function u times v. So we can integrate the left-hand side very easily. And then the right-hand side is just the integral of u prime times v plus the integral of u times v prime. So we then pull things over to the other side, and we can solve, and we get the integral of u dv. And the dv here is just, you should view that as the v prime of x dx, is just going to be our integral of uv prime evaluated at a and b. So that's the boundary term, u of x v of x at b minus u of x v of x at a minus the integral of v du. So integration by parts, u substitution, these are going to be the integration techniques that we will probably use the most in this class. So it's a great example of how powerful this is. Let's look at the integral from 0 to pi of x cosine of x. So when you're doing integration by parts, it's really not that bad because there are not too many options. I need to choose u and I need to choose v. So u is probably either going to be x or cosine of x. Does anybody know why I chose to make u of x equal x and not cosine x? So why would I choose u of x to be x?
Because it's simpler to differentiate than integrate, where cosine or sine doesn't get any simpler depending on if you choose it for u or v.
Well, if I choose u to be sine of x, its derivative is easy. So both of these functions are easy to differentiate and integrate. So it's not just that they're easy, but what happens to x when we differentiate it? It becomes 1. It becomes just dx. If we integrate it, what do we get?
One half x squared.
1/2 x squared. So the degree would go up, and that would give us a more complicated function. So I know how to integrate cosine of x or sine of x. What makes this problem hard is the presence of the x. So I have two choices. I could do x or I could do cosine of x for u of x. But if I had dv be x, then v would become 1/2 x squared, and then that would make the problem worse. So it's much better to do it this way. And I get 0 plus cosine of x evaluated at pi and 0, and I get -2. So the first question you should always ask is this reasonable? So when you look at this integral, are you surprised that you get a value of -2? Well, if we look at a plot, your cosine starts off at 1, it's 0 at pi halves, and then it becomes -1 at pi. The function x is 0 at 0, and it's increasing to pi at pi. So when you look at the product of the two functions, when cosine is positive, x is smaller than when cosine is negative. And so I would expect that this to be a negative integral. So before I do any calculation, just looking at this, I expect my answer to be negative, and this gives me a chance of trying to detect, any algebra mistakes. Always on the lookout for finding algebra mistakes. We also know that the smallest, the most negative we could be is -pi. And so we know the integral is somewhere between 0 and -pi squared. And as an aside, I say you could actually probably improve it to -1/2 pi squared. So again, whenever you look at problems, try to get a rough feel for what the answer should be. Okay, so here is an interesting one. This is a really nice integral. I want to integrate from 0 to infinity of x e to the negative x squared over 2. And so if I do u substitution, I can take u to be x squared over 2, and then du is x dx. And so when I plug this in, I'm able to do the integral without any trouble. What if I gave you the integral from negative infinity to infinity of x e to the negative 4x squared? I could say, well, let's play a similar game. Let's let u equal 4x squared. And if I take that to be 4x squared, du would be 8x dx. So this is almost what I have. I have to put in this factor of 1/8, not a big deal. And I would just get 1/8 e to the minus u du. And I have to be careful. This is not valid. Can anybody tell me what this integral should equal?
Is it 0?
It's 0. Why is it 0?
Because we're going like half of it is negative and half of it is positive, and then the exponent, that term always works out to be positive.
Right. The key word is we have an odd function. So the integral is 0. It's more than just that it's negative in one part and positive in another. It's that they perfectly balance. F of negative x is negative f of x. They cancel each other out. And so what went wrong? And so the danger is when we did the change of variable, we weren't careful. If we take u equals 4x squared, when x goes from minus infinity to infinity, we get u goes from infinity to infinity. You can't do that. So one of the points they often don't emphasize enough when they do the change of variable theorem is that you need a one-to-one transformation. And so the problem here is we had something that was 2 for 1. Is when you look at what was going on, 2 different values of x went to the same value of u. And so if we wanted to do this u substitution trick, what we would have to do is we would have to break the integral up into 2 different integrals, minus infinity to 0, and then 0 to infinity. And then if we do that, then everything is okay. All right. Any questions on this integration? All right, as long as we're doing integration, let's do one of the most important integrals of all time, the Gaussian integral. And this is extremely famous. So let's let f of x be e to the negative x squared. And then eventually we'll see what's called the normal distribution. So a normal random variable with mean, mu, and standard deviation sigma. I'm assuming everybody has seen these terms before. If not, don't worry. We will definitely talk about what they are later. That would have density, we'll say f mu sigma of x is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. And so for probability density, you have 2 properties. The integral from minus infinity to infinity of f of x dx equals 1, and f of x is non-negative. And then if I look at the area under the curve from A to B, this is the probability we get a value between A and B. What we're going to do is we're going to prove the integral from minus infinity to infinity of f of x dx equals 1. And once you have that, it's not too bad to show that the integral of f of mu sigma x dx equals 1. This is just by changing variables. So you should make sure that you're comfortable enough doing these simple change of variables that I can translate x that I can rescale. So again, you must make sure you're comfortable doing. Okay, you need to make sure you can do that. If you can't do that, please let me or the TAs know immediately. So I'm going to just look at the integral of e to the negative x squared. So let's let I be defined to be the integral from minus infinity to infinity of e to the negative x squared dx. So I squared is the integral from minus infinity to infinity e to the minus x squared dx, integral from minus infinity to infinity e to the minus y squared dy. I'll just use a different variable. Because when I integrate, I'm integrating out the variable. It's a dummy variable. So I need to do this double integral. Does anybody know what class number real analysis is?
350.
350. And this is 341. So this is a pre-core class. So in later classes, you will justify all of this stuff. Right now, what I'm going to just say is this is the same as just doing this double integral, e to the negative x squared plus y squared dx dy. And now we're going to do polar coordinates. So if x and y go from minus infinity to infinity, r goes from 0 to infinity, and theta goes from 0 to 2 pi, and dx dy goes to r dr d theta. But you should really view this as dr times r d theta. Because if each of these are in meters, theta is unitless. So dr d theta would not be an area. The fact that it's r dr d theta and not 2r dr d theta, that's different. You know, in spherical coordinates, you actually have a sine of one of the angles coming in, and the physicists and mathematicians sadly have different conventions as to how you orient things. So this is the same as the integral. Theta goes from 0 to 2 pi, r goes from 0 to infinity, e to the minus r squared over 2 r dr d theta. Well, I can write this as the theta integral because I'm integrating over a rectangular area. And this is one of the things that's really nice about polar coordinates. In polar coordinates, you start off with a circle in xy space, and that becomes a rectangle in r theta space. And so I have my d theta integral and I have my r integral. Can somebody tell me what the theta integral is? So I'm integrating d theta from 0 to 2 pi. What do I get?
2 pi.
2 pi. It's one of the nicest integrals you can do. It's just 1 evaluated in 0 and 2 pi. And now I have e to the minus r squared over 2 r dr. If I let u be r squared over 2, then du is 2r dr over 2, or r dr. Oh, I live well. Yeah, the 2's even cancel. And then, whoops. I'll get the screen back. And then r goes from 0 to infinity, becomes u goes from 0 to infinity. This just becomes the integral u goes from 0 to infinity, e to the minus u du. And so I'll just get 2 pi e to the minus u with a negative sign at 0 and infinity. So that just becomes 2 pi. So I squared equals 2 pi. Therefore, I is the square root of 2 pi. And we've evaluated the integral. This is one of the most amazing techniques I know. How do I know that it's the positive square root of 2 pi that I should take and not the negative square root? Well, if you look at I, what can you tell me about the integrand? What can you tell me about e to the negative x squared? What kind of number is that?
Always positive.
Always positive. So because the integrand is positive, I'm not going to integrate a positive number and get a negative number. So I know it has to be the positive square root. All right. So the last thing I want to do for today is sniffing out formulas. So I want to try to figure out what is the probability of A union B as a function of the probability of A, probability of B, probability maybe A intersect B. And you've hopefully seen like Venn diagrams. Here is A, maybe here's B. This region over here is going to be A union B. And so you would get that the probability.
Isn't that A intersect B?
That's right, A intersect B. Sorry, thank you. Oops. A intersect B. And so we would get that the probability of A union B would be the probability of A plus the probability of B minus the doubly counted A intersect B. And so this is a nice direct proof of a formula for the probability of the union. Then you could ask, what's the probability of A union B union C? Or the probability of A1 union AN? Are there nice formulas for the probabilities of these unions in terms of the simpler events? And so what we could do is we could maybe conjecture maybe the probability of A union B is a nice function of the probability of A, the probability of B, and the probability of A intersect B. So maybe we'll call this alpha, beta, and gamma. Now, there's no reason that this formula has to be true. Maybe it could also involve the probability of A squared and A cubed, and et cetera. So the question is, can we sniff out a formula like this? Can we try to figure out what might be correct? And so this is one of the most useful skills you can get, is to try to feel your way to an answer. So we want to study special cases. So let's study special cases of AB, with A and B living in some space omega, with the probability of omega equals 1. So if you want, the way you should view this is really whenever I have two sets, or any number of sets, they live in some universe of discourse. And that's my set omega with the probability of omega equals 1. Can somebody give me an interesting pair for AB? You have to give me a value of A and a value of B. So what would be a good choice? So if A is random, can somebody give me a good choice for B? There's actually 3 natural choices for B. What's a natural choice for B, where you can calculate all these probabilities in terms of the probability of A?
1 minus A.
So one possibility would be B is a complement. Then the probability of B would be 1 minus the probability of A. What's the probability of A intersects B? If B is the complement of A, what's the probability that you're in both?
0.
0. What's the probability you're in the union?
1.
1. Can you give me another good choice for B?
The empty set.
The empty set. Now what's the probability of B?
0.
0. What's the probability of A intersects B? You're in A and B.
0.
And so the probability of A union B is just the same as the probability of A. There's another good choice for B. What's another good choice for B?
Omega.
Omega, the whole thing. Now what's the probability of B?
1.
1. What's the probability of A union? I'm sorry, A intersects B?
Okay.
Oh,
Probability of
probability
just-
of A.
It's just the probability of A. And what's the probability of A union B?
1.
1.
And there's one last choice for B that's actually good for if I give you A. There's one more natural choice for B.
Okay.
A. Then the probability of A is A, the probability of B is A, the probability of A intersects B is the probability of A, and the probability of A union B is also the probability of A. And I claim that we know something about alpha and beta. If such a formula like this is to be true, I claim there must be a relationship between alpha and beta. What must the relationship be?
They have to be equal.
They have to be equal, as the probability of A union B is the same as the probability of B union A. There's a symmetry. So I'm looking at this, and over here, I have my alphas coming down here. I have my alphas coming down here. I have my gammas coming down here, and I want the sum to be this. So any thoughts about, well, I now have several equations with 2 unknown variables, right? So the first one, if we let P equals the probability of A, we get alpha P plus alpha 1 minus P equals 1. The next equation is alpha P equals P. The next one is alpha P plus alpha times 1 plus gamma times P equals 1. And then the last one is alpha P plus alpha P plus gamma P equals P. So when you look at these, can you figure out what alpha and gamma must be? Which equation gives us alpha?
Second one.
Second one. So this tells us that alpha equals 1. Now that we know alpha equals 1, we can go into the first one, and that's consistent. If alpha equals 1, if we now look at the last one now gives us that gamma equals -1. And if we look over here, if alpha equals 1 and gamma equals 1, it's consistent. So we get alpha equals 1, gamma equals -1. This is not a proof, but we now have a conjecture for what the probability of A union B should be in terms of the easier events. And this is one of the things I really want you to get out of this class, is how to make conjectures like this. All right, so this is a good place to stop. I am going to stop the recording, but I will stay on for a couple of minutes in case anybody wants to chat a little bit.